Okay, we're now moving into section 7.3 of the text, which is integration using trig substitution. So this is a little different than integrating trig functions. We'll see the differences as we look at an example. So where this might be useful is if we wanted to do something like find the area of an ellipse, right? So if I'm looking at this ellipse, it looks like, hopefully you remember this, it looks like it has a major axis of 3. So we can say that's x squared over 3 squared, or 9. A minor axis of 2. It's centered on the origin, so y squared over 2 squared, or 4, must equal 1. If you do a little bit of algebra, we can determine what this is in terms of y, because what we're going to want to do to find the area of the ellipse is make little slices, little rectangles in this first quadrant. We can get a quarter of the area more easily looking at the first quadrant and then multiply that by 4. So that would be an excellent way to figure out what the area is. So we want to solve for what y is in the first quadrant. I'll just quickly go through that algebra. Y squared over 4 is equal to 1 minus x squared over 9, which means that y squared over 4 is equal to 9 minus x squared over 9. Feel free to pause if you need to contemplate any of these steps. So y squared is equal to 4/9 times 9 minus x squared. So y is equal to 2/3. We're taking the square root of everything. This is the square root of 9 minus x squared. So that would be the top of the curve up here. All right, we would need the negative of this if we were working on the bottom half of the curve. But let's just work with the top half. So now we want to find the area of this. So we could say that a quarter of the area of the ellipse is equal to the integral from x equals 0 up to x equals 3 of the equation we just found. So we'll put the 2/3 in front. And then we have the square root of 9 minus x squared with respect to x. Now, when you look at that, you should probably first run through our little list of things we know how to do. And you always start with the memory list. That is not on the memory list. Can you do any algebra? There's no algebra you can do to make it fit the memory list. Use substitution. You might want to try it, but it doesn't get you anywhere. So you would probably substitute for 9 minus x squared, but the derivative of that would cancel out if you did use substitution. This is clearly, if we look at the next thing we did, integration by parts. That requires there to be 2 factors, a u and a dv. This has everything under the square root, so you can't do that. It's clearly not a trigonometric expression, so we can't use the methods of the last part, and this is not a partial fraction. To use partial fractions, it's not a partial fraction problem, I should say. There would have to be a rational expression. So everything that we know is off the table. We need a new trick. Here's the new trick. This is in the form that we have, so new trick. The integral has an integrand that has an a squared minus an x squared in it, okay? So the new trick is let x equal a times the sine of theta, all right? Now, why does that work nicely? Because then what this leads to is the square root of a squared minus, if you square a sine theta, you get a squared sine squared theta. That will simplify to, you can factor out an a squared, in fact, take it out, whoops, sorry about that jump, out of the square root, and you're left with 1 minus sine squared theta. And hopefully you remember that since sine squared theta plus cosine squared theta equals 1, 1 minus sine squared theta would just be the cosine squared of theta. So this is just a times the cosine of theta. Likewise, dx d theta will be a times the cosine of theta. All right, so you can say dx is equal to a times cosine theta d theta. So we can rewrite the whole integral in terms of what dx is and what x is, and things will simplify down as we do that. So for this particular problem, the a value is 3. A squared equals 9. So for this particular problem, let me do this in blue. We would want to say that, let me rewrite the problem. The quarter a is 2/3 integral from 0 to 3 of the square root of 9 minus x squared dx. If we let x equal 3 times the sine of theta, a lot of good things will happen. All right. So the first thing that happens is dx d theta will be 3 cosine theta. So dx will be 3 cosine theta d theta. So that's something we can substitute for dx. Now we have limits on this problem. So if I want to, I need to change the limits to limits for theta, because we're going to be changing this. There will no longer be a dx after the substitution. There will be a d theta. So the limits for x had been 0 and 3. So let's look back up at the equation and determine what values of theta will give us the corresponding values of x. So if I want x to be 0, clearly the sine of theta needs to be 0. So the sine of 0 is my best guess for that, right? If I want x to be 3, the sine of theta needs to be 1, and that happens at pi over 2. So I'm ready to rewrite the whole problem. I can say that 1/4 of the area is 2/3. The integral from 0 to pi over 2. So theta equals 0 to pi over 2 times the square root of 9 minus, when we square what we subbed for x, we'll have 9 sine squared of theta. And instead of dx, remember to put all of this in for dx, 3 cosine theta d theta. You have to put in the whole expression there. Don't just write that dx equals d theta. It does not. All right, now this will simplify greatly. This is 2/3, the integral from 0 to pi over 2. Let's do this in steps. We'll have, when you factor out the 9, from out of the square root, we could have a 3 times 1 minus sine squared of theta. That's what will be left inside. We'll still have a 3 times cosine of theta d theta. All right, that will simplify. We have 2 factors of 3. We can bring those out. So right now we have 9 inside the integral. Let's bring it outside, and that gives us 18/3. Let's just go. That's going to be 6. All right, on the outside. So if I bring all of the constants out, I'll be left with 2/3 of 9, or 6. And then the square root of 1 minus cosine squared could be rewritten as, 1 minus sine squared is the square root of cosine squared, which is a cosine of theta. But then we have an extra factor of cosine theta, so we have a cosine squared of theta d theta. Now this takes us back to the last section where we did integrals of trig functions. So we can, if you recall, cosine squared of theta could be rewritten as 1 plus the cosine of 2 theta over 2. So if we bring the factor of 1/2 out, again, we can say that we have 3 times the integral of 0 to pi over 2 of 1 plus cosine of 2 theta. So the half was brought to the outside, d theta. And at this point, we can take the antiderivative of the integrand. The antiderivative of 1 with respect to theta is theta. If it had been with respect to x, that would be an x. And then remember the quick U substitution, the opposite of a quick chain. So it's 1/2 sine of 2 theta, right? The opposite of a quick chain. So to check it, we would do a quick chain, and that would bring us back to cosine of 2 theta. We're going to evaluate that at 0 and pi over 2. When we substitute pi over 2 in, we have pi, let me put this in parentheses because we'll also substitute 0, plus when you put pi over 2 into 2 theta, you have pi, and the sign of pi is 0. So we have pi over 2 plus 0, minus, when we put 0 in, we have 0 plus 0. So that all simplifies down to 3 pi over 2. Now remember, that was 1/4 of the area. So the area ends up equaling 6 pi. All right. Now what might not be so obvious is this is actually equal to the product of the semi-major axis and the semi-minor axis times pi. All right, which is the formula that gets worked out in, I believe it's example 3 of your textbook. I'm sorry, it's example 2 in this section of the textbook, where they work it out for the general case. So you can see the area of all ellipses is just pi AB. And that makes sense because if we have a circle, A and B are equal and we call it R. So that would in fact give us pi r squared if that were a circle. So let me stop this video and actually let's derive using calculus the general formula for the area of a circle in a similar manner.